Hi there, Turgeon here, bringing you physics from afar. You know that electricity is all about electrons. We got two types. We've got electrostatics and we have electric current. One of these involves charges at rest and one of these involves charges in motion. Well, it turns out electrostatics, static means rest, static means not moving. In motion, we're talking about a flow or a current. This video is really about getting into charges in motion. You can see that's expressed with this vigorous looking active arrow thing. This is not an official entry yet. Here we've got an actual photo of a light bulb lit, and we will be looking at a simulator another time. If we make a complete circuit, it needs to have certain elements. I'll call these elements or attributes or requirements of a complete circuit. There has to be some power source or a voltage source, which we call an electric potential difference or difference in electric potential. Notice that's always got 2 points. You can't have a single end of a battery that provides what you need to make the charge flow. There needs to be a difference. There needs to be a complete path, usually a metal, to conduct from one side to the other. A load or resistance, something that the current is doing something with. Could be a battery, could be a light bulb, could be an antenna from your phone, could be a speaker. As soon as you connect this, the charges are going to start to flow, because here's my garden hose analogy. Because it's like a garden hose that's completely full. The charges are already in the garden hose. The charges are already there and they are able to flow instantly. You don't have to wait for the metal to fill up with charges. This is called a schematic diagram. Here's the battery, this symbol here. Notice that one of these ends is longer than the other. What causes electric current? Consider these 2 tanks of water with a pipe in between. What could we do to make water flow from left to right? A lot of people say you could put a pump in here. Okay. What else? A lot of people say you could add pressure to the air above here. That's true. That's starting to sound like a battery. A lot of people say, well, we could change the relative heights. Yeah, if you make this end higher than this end. Either way, whether it's pressure or changing the heights, you need to give one end more energy than the other, potential energy, which becomes kind of something like kinetic energy as that flows, and it's really the height difference that matters. It's not really about how far apart they are left to right. We have words for this. Let me first define, well, let me say this. So we call this difference, in electricity, we call it voltage. And that's, like I said before, that's an electric potential difference. Now we could decrease this current if we put these filters in. These waffle looking things are supposed to be filters. If we put these filters in, it will slow down the electrical current. But this represents an electrical current going through here. Easy teach glitches. Ha! It attached in an unintended fashion. This is electrical current going through here. Now, what is electrical current? It's a flow of charges. It's more specifically the rate at which charges flow. And it's coulombs. It's literally coulombs that are flowing. It's these electrons that are flowing. So if you imagine a wire like this, these little dots represent the electrons. They're not lined up one by one in single file. There's millions and billions across even the width of the wire, and the pressure causes those to flow. It's the electrons that flow. It's kind of like, remember that heat was caused by a temperature difference? Well, electric current is caused by an electric potential difference. These little waffle things represent resistance. These little waffle things, they would slow down the current. The more the height difference, the greater the current. Flowing charges. When they do flow, they have resistance, which is kind of like friction. That brings us to Ohm's law. It's a relationship. It's an equation, yeah, but it's a relationship between three quantities. You have your voltage, capital I is current, R is resistance. It's easy to remember because R definitely stands for resistance, V definitely stands for voltage, and the only logical thing that's left over is I for electrical current. Measured in volts, amperes, and ohms. If you write this as a statement, you can say that current is proportional to voltage and inversely proportional to resistance. Now, I'm not going to say this kid's name on a video, but a lot of you know this kid who said this a couple of years ago. I've seen you say hi to this kid. Let's do a practice problem. Now remember, please, don't just multiply stuff. Don't just add stuff. Don't just divide stuff. Just use the equation. This looks like a resistance. This looks like a voltage. Oh, I'm going to calculate I in this case. This is an unknown voltage. This looks like a resistance. It even says resistance. And the ammeter, what is that? That's just the thing that measures this. That's got to be electrical current. I just drew a schematic for this. Another, it's the connections that matter. Who cares about the shape? It's called a schematic diagram. Positive, negative end of the battery. Don't worry about the conventional current thing. We'll talk about that later, but that is true. Plug in. We don't know this value. Plug in the 1.5 and the 20. Literally write this. This is something I've been noticing lately. A lot of people aren't in the habit of putting the numbers into the equation like this. Equals, divide, 0.075 amps. Also known as 75 milliamps. It's a pretty small number. Now, in this value, we simply calculated the voltage in this second problem. So we plugged in different numbers. I, 6.4. R, 2 ohms. That's 12.8 volts. This has been, well, I was ready to say this has been physics from afar. I just want to summarize. Voltage right there causes current right there. The resistance slows it down. This has been physics from afar.